Assalamu alaikum everyone. This is Fadila, and today our topic of discussion is production equilibrium. So hopefully by the end of this video, we'll be covering a whole array of topics, including Isoquant Curve, Isocost Line, marginal rate of technical substitution, optimal combination of factors, and lastly expansion path. So without any further ado, let's begin. So today, our first topic is Isoquant Curve and Isocost Line. For some context, we know in the long run, production, that is Q, is a function of two inputs, labor and capital. Just to remind you all, we know production has mainly four inputs, land, labor, capital, and organization. But in the long run, that is in a long period of time, production is only a function of labor and capital. That is, only labor and capital become variable while the others remain fixed. Which is why it's very important to add ceteris paribus to this, meaning that all other inputs must remain constant or fixed. Another confusion that might arise is that why is there a bar over Q? That is, why is Q being considered constant? It's because we're working in a 2D space, right? That is along x-axis and along y-axis. So there's only space with two variables, and we already have that, one being labor and the other being capital. As such, Q must remain constant, as we cannot work with three variables in a 2D space. So now that we have that out of the way, let's say we want a production of 10 units, all right? This is big. This is our desired output. What are all the possible combinations of labor and capital that can give us this, all right? So let's start with the most obvious one, 5 plus 5, basic algebra. Let's say 5 is labor and capital is 5 again, all right? Let's say take another scenario where labor is 6 and capital is 4. Another scenario where labor is say 3 and capital is, let's say, 7. All right. All of these combinations equal to 10. But where do these differentiate? They differentiate in their values or ratios of L to K. That is, if L increases, K decreases, and vice versa. So the ratios keep changing, right? But they equal to the same number. And if we plot this on a graph, all right, let's say along x-axis there's L, along y-axis there's K. Let's say we input 3, 5, and 6. And along it here is, let's say, 4, 5, and 7. All right. So if we kind of plot this, we'll get somewhat like this of a curve. It's important to remember that we have only taken 5 possible combinations. To get a more detailed graph, that is a more proper one, we need at least 10 to 12 combinations. But as this is just an example, we're only taking 3 combinations. So this is what we're going to get, basically. All right. And along each of these graphs, there stays or there exists a different combination of L and K that gives us the same level of output, that is production. That is, along this curve, the production is the same, but the ratio of L to K differs. And that is exactly what Isoquant curve explains. That is, Isoquant curve is such a curve that represents all possible combinations of two inputs, let's say in this case that's labor and capital, that give us the same level of output. That is, level output remains the same, but the combinations of L and K, that is the ratios of L and K, differ and change, giving us a downward sloping graph. Let's come to the properties. We know Isoquant curve is downward sloping, as we just have seen. It's downward sloping and convex to the origin. Now, the third point is an important one. Let's say this IQ curve right here that I've drawn has a production level of 10. Again, this is hypothetical. Let's draw a curve that's higher to this, so it will have a higher value, that is 15. And if we draw a curve that's lower to this, it will have a lower level of production, that is 5. So the higher we go, the higher the level of production increases. But it's important to remember that in the same IQ, in the same Isoquant curve, the level of production remains the same. That is, for this, the level of production for each point on that curve is 15. For each point on this curve, level of production is the level of production is 10. And for each point on this curve, the level of production is 5. And that is exactly what our fourth point describes. That each point on the IQ gives same level of production. Let's come to our last and one of the most important properties, that is IQs never cross. Now let's say what happens when IQs do actually cross. Let's say this is IQ number 1 that I have and IQ number 2. All right. And let's say they meet at the point C. Now the higher IQ has a point A and the lower IQ has a point B. All right. Now, according to definition, we know A must be equal to C, right? Because each point on the same IQ gives us the same level of production. And B must be equal to C. Now, by basic algebra, we know A must be equal to B. But that's not possible, right? Because that violates our third condition itself, our third property. That is, in a higher IQ must give us a higher level of production. That is, A cannot be equal to B, A must be greater than B. So what this proves is that our initial proposition that IQs do cross was wrong, which means that IQs never cross. I hope that clears that up. Now let's move on to our next topic. Moving to our next topic, which is Isocost curve. To put it very, very simply, an Isocost curve is the graphical representation of a company's or a firm's cost constraints. That is how much budget it has to adhere to for the fiscal year, let's say, all right? Now, let's say, to put it in another way, we know there could exist an infinite number of IQ curves, all right? But what restricts the number of IQ curves or production that a company can have? Its cost line, that is its cost constraint, all right? Now let's say a company has 100 units as its cost line. That is, this is the budget that they have to adhere to. So it can either buy 60 units of labor and 40 units of capital, or it can purchase, let's say, 50 units of labor and 50 units of capital, right? So all the possible combinations that a firm can purchase of two inputs and still adheres to its cost line is known as the isocost curve. That's exactly what the isocost curve practically represents. That is, all the combination of two inputs, such as capital and labor, that a firm can purchase given total cost. And this can be explained by this graph right here. That is, if you plot, let's say, a number of combinations of labor and capital, all that equal that or that adhere to the cost line, that is the cost budget that a company has, we get this kind of a straight line. All right. And this can be explained by the equation right here. Here, cost, C is cost, and wage is the cost of labor, and interest rate is the cost of capital. That is, cost equal to labor and the price of labor, or plus capital and the price of capital. That is, each input along with its cost, that is the summation of each input along with its cost, is basically the cost. Now that we know what isoquant and isocost curves are, we can move to our next topic, which is producer's equilibrium. All right, so let's say this is our IQ curve, okay? And this is our graph, and we draw a number of IQ curves, all for the same firm, all right? Okay, let's fix the last one. It's a bit crooked, and as we know, IQs don't cross. So yeah. So these are the three levels of production that a firm has, let's say, hypothesized for itself, all right? And a firm's cost line is somewhere right around here, all right? And this is our IQ curve number 1, this is our IQ curve number 2, and this is our IQ curve number 3. Now, Undoubtedly, IQ curve number 3 gives us the highest level of production, but it is beyond our cost line. That is, to simply afford that amount of production, a company will have to outstrip all its budgets for the fiscal year, right? And that is not pragmatically possible for any company. So number 3 cannot be our ideal scenario, or our at the point where a firm will maximize its profits, as the firm cannot simply afford it. Let's come to IQ curve number 1. Now the IQ curve number 1 is, let's say, right here, right? So yeah, so it should be IQ curve number 1. So it's well within our cost line, right? Because it's intersects it, but it does give us a lower level of production. So let's just keep it into consideration and we'll debate and we'll come to a conclusion later. And let's go to the remaining one, that is IQ curve number 2. Now, IQ curve number 2 is also within our cost line as it is, as the cost line becomes tangential to it. And it gives us the higher level of production at IQ number 1. So at IQ number 2, the firm will maximize its profits, and it can also purchase the inputs given its cost line that has, let's say, decided for the year. All right. So IQ number 2 is our ideal situation, right? And the point at which IQ number 2 is tangential to the cost line is basically our equilibrium point. That is, E is basically our equilibrium point. Now, why is only E the equilibrium point? A, B, and E, all of these intersect the cost line, right? But why only E? That is because E is on a higher IQ curve, right? So that means it gives us a higher level of production. Also, it is tangential to the isocost line. And the slope of the IQ curve at this point and the slope of the isocost line becomes equal, which is what is explained right here. Due to all of these conditions, as all of these conditions are met only for E, not for B, not for A, only for E. As such, E is our producer's equilibrium. That is, E is the point at which a firm maximizes its profits, given the number of inputs that it can purchase and the output that it can produce accordingly, and it will have no incentive to change its output level because it's already maximizing profits. So now that we know what producer's equilibrium is, let's move to our next topic, which is marginal rate of technical substitution. Okay, now we have been discussing from slide 1 itself that in the long run, production is a function of labor and capital, while all the other remain constant, right? So let's say we want to swap 1 unit of labor for 1 unit of capital, right? The rate at which the swapping or substitution happens is marginal rate of technical substitution. Now, I know this sounds a bit kind of jumbled and confusing, so let's put it simply and let's use an example. Let's say a company has 100 units in total, all right, 100 units of inputs. Among this, 60 is labor, 60 units is labor, and 40 units is capital, all right? But a company doesn't want this ratio. It wants something like, let's say, 50 units of labor and 50 units of capital. All right. So what it is basically doing is swapping 10 units from labor to increase 10 units in capital, right? This swapping, this substitution is known as marginal rate of technical substitution. That is the rate at which one input, say capital, or say like labor, can be substituted to another, let's say capital, while keeping the total output constant. That is, let's see here, 60 plus 40, this equals to 10, and this equals to 100, and this also equals to 100, right? So that means our output level must remain constant, but the ratios can be changed, right? It can be substituted. And this is exactly what the data set here illustrates. So let's say we have all of these combinations, A, B, C, D, and E. For, let's say, combination number A, we have 1 input of labor and 10 inputs of capital, all right? And as we progress downwards, we see the units of labor is increasing and the unit of capital is decreasing. That is, we're swapping capital for labor, right? So MRTS can be described as the ratio of the change of K to the change of L. See, let's see it right here, all right? So if this is change of K, that means del K to del L, right? So let's see, what is the change of capital right here? 5, right? That is, since 10 minus 5 is 5, and the difference of 2 and 1 is basically just 1. So our MRTS, by definition, should be change in capital, that is 5, to change in labor, that is 1. All right? See? It matches. So let's say for 5 and 3, the difference is 2, and for 2 and 3, the difference is again 1. Difference is 1. All right? So this becomes 2 by 1, that is 2. And in this way, the change in one input to the change in another input is the way MRTS is basically described or explained. Now that we know what MRTS means, let's dig a bit deeper into this topic. So we know in an IQ curve, like in the long run, production is a function of two inputs. That's basically what we have been saying since the start of this video. Let's say we want to partially differentiate left-hand side and right-hand side. All right. Now, to give you all a basic definition of partial differentiation, it means, uh, let's say we are partially differentiating with respect to x. That means, except x, all of the variables are to be considered as constant, and we differentiate according to that. All right. Now we know that Q is production. So if we partially differentiate Q, we get marginal production. And if we differentiate this, once we have to differentiate once with respect to L, that is K is held constant, and once with respect to K, that is L is being held constant. All right. Now we see this result is 0. Now what does this mean? What this means is that the marginal production is equal to 0. Now what is marginal production? Marginal, to put it very easily, the extra output that a company or a firm achieves by incorporating or employing one extra unit of input in the production is what marginal production and is basically all about. So that is in an IQ curve, the marginal production is 0. That is, there's no difference of production. That is, there's no increase of production or there's no extra units of production that is being produced. And that is one of our basic properties of an IQ curve. That is, along the IQ curve, the production remains the same for each and every point. And that is exactly what's described here, that each point on the IQ curve gives us the same level of production. Now, let's say we want to find out the slope of an IQ curve. Now, this is what we have found out, right? Now, if we want to put this in the form of y equal to mx plus c, that's basically what we have learned in straight line, right? How to find out slopes. If you want y equal to mx plus c, where m is our slope, and we incorporate this equation and we arrange it in such a way, we'll get this. We'll get this right here. That is, the slope of an IQ curve, that is del K by del L, is the partial derivative of production once with respect to L divided by partial differentiation or derivative of production with respect to K. Now, we know partial differentiation of production is always equal to marginal production. So it can be described that this is equal to marginal production of L, that is labor, and this is marginal production of K, that is capital. Now we know MRTS can be explained as the change in K to the change in L, right? That is basically this. As such, we can say that del K by del L That is del K by del L is equal to MRTS, right? That is MRTS is equal to marginal production of labor divided marginal production of capital. Now, let's say we want to find out the slope of an isocost line. Now we know isocost line can be described as the price of labor multiplied with labor and the price of capital, that is interest, multiplied with capital. And if we rearrange this in a form of y equal to mx plus c, where m is the slope, we get basically this equation. That is, the slope is equal to the price of labor, that is wage, divided by the price of capital, that is rent. Now if we equate both this equation, that let's say this is equation number 1 and this is equation number 2, we're going to get this equation right here. And that is this right here, right? And let's say this is equal to a constant C lambda. The reason why we're equating this to a constant is because we use this formula right here to find out optimal combination of factors, which we'll be discussing about next. Okay, so let's say we have an IQ curve right here and a cost line right around here. So since the IQ curve is tangential to the isocost line, this must be our equilibrium point, as we have discussed in Producer's equilibrium. And along x-axis, as always, we have labor, and along y-axis, we have capital. Now if we draw a line extending from the equilibrium to x-axis and a line from equilibrium to the y-axis, we will get L star and K star. That is, this is our optimal labor and this is our optimal capital. That is the best case scenario, in other words. That's it. That is the mix of inputs that a firm uses to produce specific output, that is our desired output, by still adhering to the cost line, that is the lowest possible cost that a company or firm can employ, is basically the optimal combination of factors. That is, by employing L star and K star, we will get max output, that is Q star, which basically says that we will get max profits. All right, and that's exactly what's explained right around here, that this is IQ curve as this is tangential to the isocost line, and this is our equilibrium point right here. That means at this point, if we employ L star, that is right, this is this L star, and this K star, we'll get Q star, that is our optimum production. That is the max production that a company can achieve given its cost constraints, given the number of inputs it can purchase, and given the output it can produce accordingly. Okay, now our next topic is expansion factor. So let's say Alright, so let's say we have a graph and it has multiple isoquant curves. When a graph has more than one isoquant curve, it's known as an isoquant map. So for each of those isoquant curves, there must be an isocost line, right? Considering ideal situations, all right? So if it has an isoquant curve, it must be tangential to it. The conjugate produces equilibrium, and it must have an equilibrium point, right? And the line that passes through all of these equilibrium points is known as our expansion path. That is, if we define in terms of economics, a concept of economics that traces the cost-minimizing combination of inputs a firm will use as its output levels increase. That is, let's say, this was the initial cost line of a company. And as it becomes more successful, as it expands, its cost constraints decrease. As a result, its cost line gets higher, right? And its budget basically increases. So as its budget increases, for each of its cost lines, there must be an ideal level of production, right? And if it's an ideal level of production, there must be an equilibrium point, let's say these, right? So the line that passes through all of these equilibrium points is basically the expansion path. That is it shows all the possible combinations of capital and labor a company will use as its output level increases as a consequence of its budget increasing. That is, its cost line gets higher up. So that was it for today. Thank you for watching. If you like this video, please like and subscribe.